Balance the following chemical equations and classify them as either combination, decomposition, single replacement, or double replacement. In the first reaction, we have sodium reacting with chlorine to form sodium chloride. If we look at our sodiums, we have 1 on each side, so they're balanced. The chlorines, we have 2 on one side and 1 on the other, though. They're out of balance. A coefficient of 2 in front of the sodium chloride now makes the chlorines balanced. But it does mess up the sodiums that we just verified were balanced. Now we have 1 on one side, 2 on the other, so a coefficient of 2 in front of the sodium on the reactant side is required to balance the reaction. In this problem, we have 2 pure elements reacting to form a compound. This would be a combination, or sometimes books call it synthesis as well. The next problem is a little bit more fun. We have I4O9 reacting to form I2O2 and I2O6. So all of these compounds have iodine and all of them have oxygen. Where do we begin? Well, in a problem like this, one of the first things I'm going to look at is looking at the iodines. I know I have 4 on this side. So between these two, I need to have whatever number I have between these two add up to the same number that I have on the other side. So if I have a 3 and a 5, that would have to be 8 in order for the iodines to stay completely balanced. I can also look, if I took the I4O9, if I weirdly was able to divide it in 2, it would be like I2O4.5. Well, this 4.5 is actually quite a bit closer to 6 than it is to 2. Well, a little closer to 6 than it is to 2. So, if I'm going through and guessing numbers to place inside here, I'm going to think that I probably should have a little bit larger number on this one than this one, but not night and day different. So if I look at it, let's try 8. So if I needed 3 and 5, that would give me 6. So 3 times 2 is 6. 5 times 2 is 10. That would give me 16 iodines on this side. I could go through and call that 4 of the I4O9s on the other. This gives me 16 iodines on both sides. Now, if I look, the 4 times 9 is 36 oxygens. On the reactant side. And if I look, I also have 3 times 2 and 5 times 6. So 6 plus 30, 36 oxygens on the product side as well. We are now balanced. Now, since I start with a single compound and I end up with 2 simpler compounds, this would be a decomposition reaction. In the next reaction, we have magnesium reacting with water to form magnesium hydroxide and hydrogen gas. In fact, magnesium, such as what you might find in like a fire starter stick, will actually react with warm water, actually pretty warm water, in order to form a tiny bit of hydrogen gas. It's not a fast reaction, but under the right circumstances with freshly exposed magnesium, it can be done. So I look at this, I only have one element that's not hydrogen or oxygen, and the magnesiums are already balanced. So I look at the hydrogens. I have 2 on this side, I have 2 on this side, plus another 2. So 4 altogether. I need to make 4 hydrogens on the reactant side. Now, that didn't change anything about my magnesium, so I'm still good there. It did make 2 oxygens, but that's okay because I have 2 oxygens on the other side. We are now balanced. A single element, or a pure element, reacting with a compound to make a different compound and a different pure element, that is a single replacement reaction. And finally, we have scandium-2 nitrate reacting with potassium dichromate to form scandium-2 dichromate and potassium nitrate. So if we look at this scandium, there's 1 on each side. If we look at the nitrogens, we have 2 on this side, only 1 on that side. So I need a 2 in front of my potassium nitrate. I have 2 potassiums on this side, so my potassiums are good. I have 2 chromiums, 2 chromiums. I have 6 plus 7, 13 oxygens. 7 plus 6, 13 oxygens. This one is now balanced. And because we have 2 compounds reacting to form 2 different compounds, this is a double replacement reaction.